Hello, I'm Yegor Prikazuk, and this is the user guide of SCOPE, Soil Canopy Observation of Photochemistry and Energy Fluxes model. We are going to talk about leaf biochemical models, and you will learn how to run single leaf simulations with SCOPE, the famous modularity of SCOPE. What I expect you have already done is you went to our GitHub and you downloaded the model with download zip. After that, you have unzipped the file, and now you can navigate to SCOPE Master, and you see these files. Also, of course, you have MATLAB, which would normally start with double click of SCOPE. See that the SCOPE is open, and we run it for the first time. The first run has 100 simulations, and hopefully you get the same message that the output is the same as in the verification dataset, which means we are good to go. What I also expect you to do is to find our documentation. The link is directly in the README. Two options that we are going to discuss today are described under options of fluorescence model. So when you switch it from 0 to 1, you change to biochemical models, and today we are going to learn about the differences between them. And applied temperature correction is another option that we will cover today. Going to SCOPE, in fact, the SCOPE itself we don't have to run because single leaf simulations will have to parameterize ourselves. For that, I have prepared a small script that will do the job. This is very useful when you use data from, for example, gas exchange devices, for example, LICOR or BALT, that give you CO2 and light response curves. And this is how you can tune them. First of all, we are working at leaf level, so we don't want VCmax to differ from the one that we set. So the FV, the exponent of the logical decline of VCmax, is set to 1, so there's no decline. Then, among options, we usually want to apply temperature corrections because the results are more realistic. And among constants, we only need 3 constants: the gas constant R, and the specific mass of air, and molecular mass of the air. Now, important part: leaf response to changes in environmental factors, which is called meteor. What we're providing to the model is the light, temperature, CO2 concentration, relative humidity, oxygen concentration, and atmospheric pressure. Notice that this is leaf temperature. This is absorbed by chlorophyll R, so photosynthetically active radiation absorbed by chlorophyll in micromoles of photons, units. So normally this is provided by a Flaspect model and RTMO, of course. CS is the boundary layer CO2 concentration and the boundary layer humidity as well. And of course, there are biochemical parameters, and here comes the difference of the two models. First of all, we have to say which type of leaf we are working with: C3, like majority of the crops, or C4, like for example corn, that are more adapted to dry environments. Then, in any case, there is Farquhar, von Kammer, and Berry model inside, so we have to provide the key parameters such as maximum carboxylation capacity at 25 degrees, the respiration as a fraction of this respiration rate, and the Ball-Berry model in the version of Collatz is also in both models. We have to provide Ball-Berry slope and Ball-Berry intercept. The difference comes in the simulation of the energy partitioning, and for that I would go back to the slides and remind you that when light is absorbed by photosystem, it can go to photochemistry, it can go to fluorescence, and it can go to other two sources, which is heat dissipation. One is non-regulatory, basal, and the other one is light-induced, regulatory. The case here are rate constants, and phi's are the photochemical yields. Photochemical yield of chemistry, photochemical yield of fluorescence, and others. Photochemical yields, they sum up to 1, obviously. So the two models are different in terms of Magnani model and Van der Tonde model, in terms of which component they are simulating and which component they are adjusting based on the other ones. So in Van der Waals model, the Kn component, so this light-induced regulatory heat dissipation, is fitted as an empirical curve. So the rate constant of this dissipation is fitted with these three parameters with a sigmoid curve. And after that, the others are computed. Here, a stress factor is introduced, so we can reduce Vc max further if we want at leaf level. And the temperature correction is done with a set of functions that are similar to CLM4, Community Land Model 4. For Magnani model, the adjustments are happening at Kp and Kd level, so photochemical and basal heat dissipation, with help of QL and Q and PQ, the parameters that can be measured with, for example, pulse amplitude modulation. Beta is a fraction of photons partitioned to photosystem 2. It's also present in Van der Waals model, it's hard-coded inside. And the temperature correction is based on the mean annual temperature that the plant experiences compared to the Arrhenius functions in the other model. So if we want to simulate light response curve, we say that we provide light in values from 1 to 2000 micromoles of photons per square meter per second, and we keep carbon and temperature at the same level. So let's run it and see the difference. The blue curve here is a fluorescence model of Van der Waals, and the red curve is fluorescence and photosynthesis biochemical model of Federico Magnani. You see, the net photosynthesis, electron transport rates, terminal conductance, they respond in a similar way in the models, as well as the photosystem 2 photochemical quantum yield. But the steady-state fluorescence, so the Fs as well as the eta, so steady-state fluorescence normalized by the dark-adapted fluorescence, they exhibit different pattern. The sigmoid curve for Van der Waals model, and also kind of sigmoid curve in the Magnani model. This is a response of fluorescence and other parameters to light. If we now want to make CO2 response curves, and we have to turn back light to some level that drives photosynthesis, let's say 500 microvolts of photons, then CO2 concentration and the boundary layer I sample from 0 to 1000 ppm. Leaf temperature we leave the same, and running that, we'll see these sort of responses. Still, the blue curve is Van der Waals model and the red curve is Magnani model. Net photosynthesis, electron transport, terminal conductance, photosystem 2, photochemical quantum yield. Still response in the same way. The steady-state fluorescence and the ETA are completely in the opposite way. At some point, at 500 micromoles, the Magnani model saturates, and then it exhibits the constant rate. The Van der Waals model seems to be irresponsive to the change in CO2 concentration for the steady-state fluorescence. Finally, for temperature responses, we are returning back light and CO2 to default values, and spacing linearly temperature and plotting it on the x-axis. And we see these sort of responses. Again, net photosynthesis, electron transport rates, terminal conductance, photochemical yield of photosystem 2. They respond in a similar way. And here is another difference between Van der Waals model and Magnani model. In Magnani model, fluorescence is heavily influenced by photosynthesis. It even has the light response limitation or CO2 response limitation. And that is probably why the curves are so similar to the photosynthesis curve. Whereas in Van der Waals model, it seems that there is very limited response to temperature, only changes of fluorescence. We can also see the applied temperature correction option effect in this simulation. So if we say that it's 0, and then we run the model, it's of course makes sense to run it with a temperature response. We will see, of course, that the response to temperature disappeared, and only the remaining correction for Van der Waals model are based on probably a relative humidity of the air and stomatal conductance that start decreasing after 10 degrees. If you want to change the option for the full model, so for the canopy as well, then you have to go to Scope Master and then input in Set Options file. This is where you can change the fluorescence model from the default one, which is Undertow, the line 6 equals 0, to Magnani, which is a fluorescence model equals 1. Don't forget to save if you made changes, and then Rascal and see the differences. That was it for today. You learned that there are 2 biochemical models in Scope, and you learned how to run single-leaf simulations. Thank you.